All right. Welcome back for the second day of the conference. Thank you for being here. Today, we're going to start with Barrett Nova. She's a full professor at USC as of 3-4 days ago. And so congratulations to her. She's going to be talking about asymptotic algebraic combinatorics. Thanks for coming, Barrett.
Thank you very much. Thank you very much for organizing this event. Thank you for being here on Saturday morning. So I'm a combinatorialist originally, or algebraic combinatorialist. So inherently, the things I'm going to be talking about have more motivation in algebraic combinatorics than maybe in probability. But there is a lot of integrability, maybe comes with the algebraic structure, and there is some probability and asymptotics. So I want to tell you about these things. So first, these numbers.
Maybe click here.
Okay.
Try.
Okay. So there are two sides to this story, at least for the current talk. One comes actually from probability, or from statistical mechanics, where we're looking at dimer covers on the hexagonal grids, and also known as lozenge tilings. So I hope that most of you are familiar with these types of structures. So here so for lozenge tilings, what do we care about? Where we care about things like limit shapes, fluctuations, things like that. So if the mesh grows to infinity, how do these lozenge tilings behave? And for on the other side, there is the algebraic counterpart, and it has to do with maybe originally asymptotic representation theory. Maybe started with Bershik and Kierov with a picture like this. So I don't know what you see here. So depending on what field you work with and what your interests are. But for me, this is a random Young diagram drawn from the Pancharel measure. And one can tell a lot of stories around just this picture. And one thing that, of course, maybe one of the first results had to do with the longest increasing subsequence in a permutation, which happened with one side of this random standard Young Tableaux. So there's this counterpart, and now so Chen gave a background talk explaining basics in algebraic combinatorics, what we care about from combinatorial and algebraic point of view, things like that. So I will quickly recap all of that, so just that we are on the same page. So the main object in our field is called standard Young Tableaux. Where does it come from? So algebraically, it comes from studying the symmetric group. These are permutations of n elements, and they form a group under composition. So, what people started studying already in the 19th century is representations of the symmetric group. So how can we see these elements, group elements, as matrices of some higher, maybe bigger size matrices? And irreducible stands for the fact that we cannot diagonalize everything at the same time and form smaller blocks in these matrices. So these are the smallest building blocks in such presentations. And so these are classical results. They are the irreducible representations are classified. So for Sn, they are exactly as many as the number of integer partitions, and then they're called the Speck modules S lambda. And so these are everything here in this talk, basically lambda will be everywhere. So this is this is one thing to remember. So lambda is an integer partition, which is a weakly decreasing sequence of positive integers which sum up to n. So when you say it's a partition of n, just mean that they all sum up to n. So one way to see this partition is the Young diagram. So every row has lots of lambda 1, lambda 2, and so on, many boxes. And if we fill these boxes with numbers from 1 up to n, so that they are, every number appears exactly once, and they are increasing along rows and down columns, we get this standard Young Tableaux. And in fact, the basis for the Schur modules can be in some sense given, but it's not really directly, but it's certainly indexed by by all the standard Young Tableaux of this shape. So already here is an example with the partition 3 to 1. So 3 boxes on the first row, 2 boxes on the second, and 1 box in the last row. We are filling it in all possible ways with the numbers from 1 up to 6, so that they're strictly increasing among rows and columns. And so the first question we can ask is how many? So how many? There is actually a very, they call it the celebrated Hook-length formula of Frame, Robinson, and Troll from at this point maybe 60 years ago, which says that the number of standard Young Tableaux is given by a product formula. So n factorial divided by the hook length of a box. So for every box in this diagram, we count basically the boxes that are in blue, so in the same row left to the right of it, and in the same column below it, plus that box. So that's called the hook. It's a nice product formula. So just to go back to probability and asymptotics, thanks to this product formula and a bunch of other combinatorial properties, it was relatively easy, let's put it this way. So it still wasn't so easy to analyze this Plancherel shape that I showed earlier and figure out how it should look like in the limit. So how a typical standard Young Tableau looks like. So we are not going to use this formula, but I just want to give you an example of something that is relatively. So the next part of the story is so we move from the symmetric group to the general linear group, and we can do the same. Basically, we can still study irreducible representations. So we take the n by n invertible matrices, let's say coefficient in a complex number to avoid other issues, and represent them as again invertible matrices of some other dimension. So there is going to be some other vector space on which basically all the matrices are. And now, if we take the diagonal matrix, so the entries are x1 up to xn, under this map, it's going to be some matrix. So in this case, we're going to study polynomial representation. So all the entries here will be polynomials in the x's. And the way we study reducible representations or the representations in general is using the characters, and the character is just the phrase. So this is going to be phi of the lambda, which is just phrase of the image of this matrix. And basically all the information is encoded with this character. So different irreducible representations will have different characters. And these are the Schur functions. So the character here is this Schur function S lambda indexed by S lambda from some variables x1 up to xn. What is the Schur function? Well, there are different ways of defining it. One way we can define it, well, using representation theory, probably the most useless way. But we can also define it with algebraically as this beautiful ratio of two van der Waals matrices, which actually is the main tool that actually make the connection with integrable probability and how you actually compute things. So this is this formula. You can also interpret it with this determinant. So these H's are homogeneous symmetric polynomials, and this formula is just telling you that these are. So this is the Lindstrom-Gesell-Vienot non-intersecting lattice path formula actually. So this also has a. If you want to study non-intersecting lattice paths, you would do this. And from combinatorial point of view, there are also positive sums of monomials. And that's actually very, very nice because every monomial is indexed by what's called the semi-standard Young Tableaux. So again, we take the Young diagram of our partition, we enter the numbers depending on what variables we have. So here we have three variables. We're going to enter the numbers from 1 up to 3. And this time we are allowing repetitions along rows, but the columns should still be strictly in green. So here is for this particular Schur function, these are all possible semi-standard Young Tableaux we get. And we get a monomial for each one of them. So the monomial is just tracking how many ones, twos, and so on. Yeah. In this semi-standard. So these are the tools. Now, what can we do with them? So one thing we can do, we can study lozenge tilings using all these things. So, for example, so here are three different situations. The lozenge tilings of the hexagon, this has been studied to death in some sense. So we know everything about this. So these are, as you can see, we can think of it as a three-dimensional picture where we're stacking boxes in the corner of a room. Or if you project it, these are tilings of three different types of rhombi of a triangular grid, which I haven't drawn here. So you can use Castellan theory as well if you want to study this, but in this case, this three-dimensional presentation is actually easier. We can make them, we can impose some type of symmetry, so have them vertically symmetric or centrally symmetric. So what this means is that if we are so vertically symmetric means that it's just a mirror image along the vertical line. Centrally symmetric is a little bit harder to see, but again, wherever we have a horizontal lozenge on the other side along this across this center point, we have another horizontal lozenge and things. And now, of course, from probabilistic point of view, you want to understand what happens when this mesh size goes to infinity.
Yeah, quick question for the one with centrally symmetric. So that line that you drew is essentially for any.
Yeah, so it's around the point.
So you can match it with any line.
You can match it.
Thanks.
Yeah. So we can try to study the various limiting behaviors. So when Carl was showing these pictures for the Aztec diamond and for the alternating six-vertex model, we can try to do this for lozenge tilings as well. So one way we can do this using this algebraic framework that I showed earlier is so we can parameterize the situation as follows. So first of all, this is only going to work if the boundary on the three sides is what's called a trapezoidal domain. So we have three straight lines and then something happening on the other side. And on the other side, we can parameterize this boundary by recording the heights of all these horizontal lozenges. So we basically take a slice, a vertical slice starting from the end and somewhere in the middle. So this is definitely going to be a partition. So there, of course, we index it in an increasing way. And so here, for example, we can do the hexagon with this type of parameterization. So if we take this partition for the boundary, these are all going to be flat lozenges. So they'll force this region to be completely flat, as well as this region on top, and then the rest is free to be filled as hexagon, whichever way we want. So this is one way we can do this. And then we can now apply some the combinatorial interpretation. So we consider these lozenge tilings and this type of domain here. On one side we have lambda, and near the boundary, if you do the combinatorics, you will notice that there is one horizontal lozenge right next to this flat boundary. You cannot have any more. Then on the next vertical line, there will be two horizontal lozenges, one below this blue one, one above the blue one. Then we have these yellow ones. So on their position, if we record their heights, these numbers will be the sequence of numbers is going to be interlacing with the neighboring sequence of numbers and so on. And because these are also partitions, we can also draw their Young diagrams. If we draw their Young diagrams like in this picture, we see that they are nesting on top of each other in such a way that if we replace, let's say, the blue Young diagram with the numbers 1, the red one with the numbers 2, and then 3, and so on, it actually forms a semi-standard Young tableau. The numbers will be weakly increasing along rows and strictly decreasing down columns. So this is where the combinatorial interpretation comes in that I was mentioning. So now if we want to keep track of what's going on somewhere in the middle, so if we fix a vertical line and the positions of the horizontal lozenges there, what is this? Well, this is telling us that the entries 1 up to k in this semi-standard Young tableau have shape given by the positions of these horizontal lozenges. And so we can calculate probability or express it. And calculate is a misnomer here, but because not everything here has a nice formula, but at least we can express it with this Schur function. So there is something called Schur function, which is basically the generating function for the semi-standard Young tableau, which we will obtain by removing some portion of it. So we can express this probability like this, and then we can form a Schur generating function, which is like a different form of a moment generating function with the extra. So instead of the monomials, we actually use Schur functions. In this case, normalized Schur functions to keep track of our probabilities. So if we take this probability distribution and we take expected value of this expression where y1 up to yk are just formal variables, we actually get an evaluation of a Schur function divided by the evaluation of the Schur function of all ones. And so what's good about this? What's good about this is that we, as I showed you earlier, there are some nice formulas for Schur functions. So we can try to use them and figure out what this Schur generating function is. So here are some formulas. So in one case, if we have a generic domain, so trapezoidal here, lozenge tilings at position lambda 1, lambda 2, and so on this boundary, then the Schur generating function is just the ratio of two Schur functions. And then if we do the symmetric tilings that are along the vertical line, then there is also a way to find the expression for it. It is given by characters of the orthogonal group, which are some generalization of a Schur function. And for the centrally symmetric is actually a normalized Schur function squared. So again, there is a formula for that expectation. Okay, so anyway, it doesn't matter exactly what these formulas are. The point is that one can actually do some asymptotics. So you can take the same Schur generating function and figure out what under some other distribution. So for example, if you take the eigenvalues of a Gaussian unitary ensemble matrix K by K, and you have this distribution along according to that, then that the Schur generating function is just this basically Gaussian. And if we do the asymptotics of the Schur functions involved in this formula that I told earlier, then under the right rescaling, we also get the same expression. So essentially, we have the same limiting moment generating function, so we can say something about the distribution, and this is that we can, for example, say here that the positions of the horizontal lozenges near the boundary behave exactly as the eigenvalues of a Gaussian unitary ensemble.
Exactly. Is this for which case? Any symmetry?
So this is for the classical case, but then it's also true for the symmetric cases because we do the same analysis.
Okay, and
the same
GUI.
The what?
It's still GUI.
It's still GUI.
Okay.
Yeah. So a little bit about how this thing works, but maybe I should not get into all the details. So we need to, these Schur functions are not as nice as the formulas are showing. You still need to do some asymptotic analysis to figure out the formulas that I showed earlier. So how can one do this? One way is to say, so take this normalized Schur function, and if there is just one variable, like k is equal to 1 and everything else is just once, we have this integral formula which one can analyze using steepest descent methods and so on. So we get various types of convergence results depending on which regime we are in. It's not important what it is on the screen, but basically one can do this. And if you have more variables, then it's actually in the limit somehow the asymptotics of this normalized function factors nicely. So here. So under various regimes of convergence, for example, the normalized Schur functions with multiple variables is the product of the individual points, and this is done using this formula, which is basically using this biodeterminantal formula. So that's why I'm saying it's so these formulas are useful, and so far we used at least two of them. So one is the semi-standard Young Tableaux, and the other one is the biodeterminantal formula.
And I have a question. Yeah. So you have this effective factorization in the asymptotics. Is this true for the normalized Schur functions, or is it true for the Schur function?
For the normalized.
And it's not true for the Schur function?
No.
Okay. So the normalization plays an important role there.
Yeah, because so I mean, as you see, so here there will be only one factor of this. And here we'll have k factors of this, and this is a huge number. So this, the value of the Schur function. So I showed you very quickly this spook length formula. If you want to evaluate the Schur function, there is also a nice product formula, which is kind of similar to the spook length formula. So this is enabling a lot of analysis to be done. Okay. And so one can do this for the symmetric, which, and in fact, one can also. So I showed you how to derive the GOE eigenvalues. You can also derive actually limit surface for the whole three-dimensional thing. That there is actually concentration around a specific surface, and in some inexplicit way, what this surface is, but we can't really write it down. And so one can still use this. This is the statement. Don't read it because it's complicated. But basically, the punchline is that in the symmetric case, the limit shape, the limit surface is the same as in the general hexagon case, which is something you would expect given that the general hexagon case, the limit surface also obeys this symmetry. So,
yeah, I got a question. So in the picture, it seems like the hexagon is symmetric itself.
yeah, so it has to be
For vertically symmetric, you can try like
so
extend.
and then, by the way, this picture is courtesy of Leo Petrov. Can recognize the calendars. It was very interesting. So actually, we cheated here because once we did I did the analysis, I realized that okay, so it's the same limit shape. So I asked him to simulate the normal lozenge tiling, and then I just cut it in the middle, and then and we forced it to be symmetric in this way. So it's like the dynamics that he uses to simulate this would not really work for the symmetric situation because it's a global symmetry. Okay, so this is what I wanted to briefly say about lozenge tiling. So this has been done. This was done a while ago, in some sense. So there have been more things on lozenge tiling developed predominantly by Vadim Borin and various collaborators. So what really asymptotic algebraic combinatorics is about, so it's more using probabilistic methods and asymptotics to figure out something that is important for representation theory and algebraic combinatorics. So I'm going to change the direction now, and any more questions on the lozenge tiling? All right. Okay, so besides these lozenge tilings, what is asymptotic algebraic combinatorics about? Well, it's not really a well-defined field, so sort of we named it in some sense. So one thing you can ask is what is the number of standard Young Tableaux of skew shape? So basically we have one partition on the outer boundary, another partition on the inner boundary, and what's the standard Young Tableaux of the shape? It's really the same thing. We are entering the numbers for 1 up to n, so that each number appears exactly once, and they are increasing along rows and down columns. It's just that the shape is a little bit different. And suppose that we let these partitions, we scale our grids. So now it depends how we want to scale it, but let's say in both dimensions, 1 over square of the fan. Then we can say that lambda is approaching some curve and mu is approaching some other curve, then what is the number of standard Young-Tableaux loss? So how well can we approximate that? And I mean, what so far what we have is the general regime. It's about square root of n factorial, but then there are lower order terms which are actually very hard to get in general. So the other thing has to do with this representation theory that I mentioned in the beginning. So there are two. So there is one fundamental problem which reappears over and over with in different contexts. So if we have some structure, so in this case, irreducible representation, and say we pair it up in some sense. So we take a tensor product of two irreducible representations. This is still going to be a representation of the same group. And if it's a representation, it can always be factored. So at least for these groups that we're dealing with, so it can always be factored into irreducible representations. So the question is how many of each type irreducible representation will we get? So for example, so if we take this B, mu and mu, these are the irreducible representations of the general linear group. We take tensor product. It's still a representation of the same general linear group. We factor it, decompose it into irreducibles. So the irreducibles are classified, so we know what they are, B lambda, and we don't exactly know how many of them there are. So the number each copy is what's called the Littlewood-Richardson coefficient, C lambda mu nu. And what we can, so instead of doing the representation theory, we can go back to our Schur functions. And this is basically equivalent to taking the product of the Schur functions and writing it and expressing it in the basis of Schur functions. The coefficient will be this C lambda mu nu. So one thing we get from the representation theory is that these guys here, they are non-negative integers. From here, it's not obvious at all. So if you take product of two polynomials, you express it in some basis, you don't really know what kind of coefficients you get. And the other fundamental type of coefficient that we're interested in are these Kronecker coefficients. So now we take the tensor product of the reducible representations of the symmetric group. Under the diagonal action, it's going to decompose into irreducible modules for the same symmetric group. And what is the multiplicity? The multiplicity is this G lambda mu nu, which is called the Kronecker coefficient of the symmetric group. And again, so we can express everything in terms of Schur functions. So now this time we can do this type of three-dimensional Schur identity, which maybe you have seen it without this extra variable C. It's much simpler. So can describe it for reference. So the original Schur identity, which is basically proven by RSK, and we use RSK to analyze subset interface particles and all sorts of things. So this is the original Schur identity. This is like a three-dimensional Schur identity, and we get this extra factor over here. And now, so Chen gave a lot of background on all of this. So what I'm going to say is basically that the Littlewood-Richardson coefficients, they have a combinatorial interpretation. They are counting some types of semi-standard Young Tableaux, which, however, it's not very efficient formula. So it actually, from computational complexity point of view, it is not. So if you want to do asymptotics, it's not very useful. But it's nice at least because it's clearly a positive thing. For the Kronecker coefficients, basically nothing is known. I mean, we know from representation here there are non-negative integers, but what do they count? Any kind of efficient way of computing it, so everything is an open problem. It's been an open problem since they were defined 18, 17 years ago. So another thing one can do is, this is the problem that I showed you yesterday in this informal open problem session. So one can do this asymptotics and fluid polynomials and so on, which in integrable probability terms is just tiling of the grid with two types of tiles which crosses what's called here elbows, so that the paths. But then there is a global restriction that paths do not intersect more than once. And now, how many are these asymptotically? This already big open problem. So now I'm going to talk a little bit about this part here in the middle. So Kronecker and Littlewood-Richardson coefficients. What can we say about them without actually having any formulas available? So one thing we can say, so there's one example where we can do type asymptotics, and it starts with the following completely unrelated problem. So this is about counting partitions which whose Young diagrams fit inside a rectangle L by M. So there is a generating function for those. This is the Q binomial coefficient. It's an analog of the binomial coefficient. It's an explicit product formula. But that doesn't really help that much with the analysis of how big these numbers are. So what turned out when we were working with the Kronecker coefficient, it turned out that this particular Kronecker coefficient M by L is just the partition M L many times. So this is a rectangular partition, and this is a two-row partition. There's actually the difference of two consecutive numbers from this sequence here. And it's not even obvious that this sequence is actually increasing up to the middle unimodal, but we somehow combining properties from the Kronecker coefficient and some other asymptotics, we were able to find this bound. And what we later did using actual probability was with Steve Meltzer and Robin Pimanto. I think Robin Pimanto was here at some point at the faculty.
Oh, interesting.
So what we did is we actually were able, using tilted geometric random variables, we were able to estimate these consecutive differences. So this is really asymptotically like a derivative of this function, and there is some expression for it, similar to the Hardy-Ramanujan formula for the asymptotic number of integer partitions, and that basically then gives us the type asymptotic for this particular Kronecker coefficient. And that's so that's as far as it goes in terms of explicit asymptotics of anything at the Kronecker coefficient. So the next thing we can say.
I have a quick question. Sorry, this is a little bit unrelated, but for the Q binomial coefficient, can you remind me when Q goes to 1, or is it when Q goes to 0?
When Q goes to 1, so
you get the binomial.
Yeah, so the Q binomial coefficient. So there is a way to define a Q integer, which is denoted with bracket Q, which is just going to be 1 minus Q to the A over 1 minus Q, which is just 1 plus Q and so on plus Q to the A minus 1.
Yes, okay, great.
And then in the binomial coefficient, you replace every, like the factorials are product of integers, you replace every integer by this Q polynomial, and then you get ratio of some polynomials, and they're all cyclotonic. So it's if you try to actually analyze this with some kind of residue type of approach, it's really bad. So it's not. Okay. So this is one example of asymptotics, and as I said, so this result here is actually using probability to do asymptotics, but I will not go into these details now. So what other questions can we ask? So basically, the simplest question you can ask is what's the maximum? So how big do these things go? So what's if we take the Kronecker coefficient absolute maximum, it turns out to be approximately square root of n factorial, which is also the largest number you can get for standard Young Tableaux with a given shape, which is the natural measure of Hershey-Kinkirov and so on. And then the maximal Littlewood-Richardson coefficient is this 2 to the n over 2. And now the question is, when do these maxima when are they achieved? And one can say a few things about it. So we can basically write a bunch of identities involving these Kronecker coefficients and proof functions with various evaluations, compared with coefficients and things like that. So we have some identities. And what we can say just from it's an existence type of results. But we can just bounding these various inequalities, we can say that the Kronecker coefficient is basically maximal when the three partitions lambda, mu, and nu are of this form. So they're the maximal partitions, the ones that give the maximal dimension or the number of standard Young. And there are some other bounds one can write in that form. What can we say about the Littlewood-Richardson coefficient? So we can so if we restrict one partition to be a partition of k and the other, so we'll have to be n minus k, so on. So this maximum is going to be between square root of n and choose k and this guys. And again, there is some type of existence result. So if we take a large partition, like so number of standard Young Tableaux of this partition is large, then there are going to be two other ones which are also large dimensional. It will give us a large Littlewood-Richardson coefficient, but things become a little bit more complicated here because you can easily make the Littlewood-Richardson coefficient 0 by just adding some boxes in various places. So this is not this problem is leaving the realms of nice integrability in some sense. So it's not very well behaved. Let's say and so something that you may be curious about is that so this paper which came out in 2020 actually used elliptical random matrix integrals and found an upper bound for for this Littlewood-Richardson coefficient with some more specifics for lambda mu and nu, and the reason that they were able to employ random matrix theory for these guys was exactly the Schur function identity that I showed earlier. And the Schur functions are also involved in random matrix. It's on the Harish-Chandra, it's on the Baire integral and so on. So what else can we say here? So I'll maybe show you some more details for this proof. So one can say that the Kronecker coefficients are bounded by this formula. So I'll write this on the board. So if we have some partition lambda, so this is our partition, L lambda is just the number of non-zero parts or the height of this Young diagram. This is of course lambda 1 and so on and so forth. So if we fix the lengths of these three partitions, we can do this type of inequality. So d lambda mu is less than or equal to 1 plus LMR over n to the power of n and so on. So it is still a pretty big number. So what kind of regimes does this make it interesting? So for example, if we have a rectangular partitions which are L by L squared. And so if this thing has n boxes, then of course L is third cube root of n. Then we can say that G lambda on so this particular rectangle is less than or equal to 4 to the n. So 4 to the n is much smaller than the square root of n factorial, which I was telling you earlier. So this is a lower bound. And how do we actually prove such a result? So the one thing I can show, again, using this Schur functions. So in this generalized Cauchy identity, so G lambda mu. So there are three sets of variables. So we have this type of expression. So what is the right hand side, which is just 1 over 1 minus xi yj dk, the product of all of this is just the generating function for what's called contingency arrays. So there's not a table anymore. Basically, x, y, and z are going to keep track of the coordinates. Let's say it's in some box, and there is a wasp here. So here in this box, we enter some numbers over here. So let's say that this number is, say, a, so in some coordinates. So this would give us a term xi to the a, yj to the a, and z k to the a. This is position ijk. And then if we expand this in terms of x, y, and z, then we get that this is going to be the number of all of this arrays, such that the marginals, if we fix the powers of x, y, and z, then we are just going to get the number of this type of arrays where the marginal, so the total sum of the entries, let's say the horizontal one, position I is going to be equal to alpha I, and so on. We could, if you slice it in the three possible directions, the sums in all the directions are going to be the marginal sum of the set. And now, basically, because so we know that these guys are positive, like the G's are positive or non-negative, and we know that these Schur functions are also positive in terms of the monomials. If we just compare monomials, so if we look at X alpha, Y beta, Z gamma, it's going to appear in some of these Schur function products, which makes it immediate that this Kronecker coefficient has to be less than or equal to whatever the coefficient was on the right hand side. So we get an upper bound of this Kronecker coefficient by contingency arrays. And how do we, and then one needs to do the asymptotic for the number of contingency arrays, which is using the technology of Sasha-Barbinok. And so it's an optimization problem essentially that would show up here. So what else can we do using again? So just using these Schur functions. So the result I showed earlier, if we fix the lengths of lambda, mu, and nu, and just let them grow directly, so the result that I showed earlier essentially boils down to this. So mu lambda mu nu is less than or equal to n to the k cubed. So if we're fixing the length of our partition, this polynomial size. And there is a notion from combinatorics. So the UP square is basically the largest square we can fit inside the Young diagram, and it has size d lambda. So if d lambda is at most k, we also get a polynomial upper bound for the Kronecker coefficient, and there is just a coefficient of k here and 4 here, so n to the 4k cubed. And in some sense, this is really the right asymptotics because, again, existence type of proof, we have no idea for which partition this is achieved, but we know that the maximal possible Kronecker coefficient, even just bounding the sizes of the partitions by k is at least, well, it's actually this polynomial, there is something explicit, so n to the k cubed. So and I must say that so in all this Kronecker coefficient, this random matrix approach that I mentioned earlier would not work for various reasons. Can discuss if you are interested. But what do we really want? We want the lower bound because we don't even know when the Kronecker coefficient is this bigger than 1. So we know some situations, but we have no idea how to get any explicit lower bound for some particular triple of coefficients. So one result is that, well, it's at least positive, it could be 0, right? So at least it's bigger than or equal to 1 when all these three partitions are symmetric. So lambda prime is the transpose partition. So if they're also it's the same partition and they're also symmetric with 1. There are some other results kind of similar to this type of contingency arrays, except that a lower bound comes from counting this number of three-dimensional partitions. So basically, you take a box, you stack in the boxes in the corner. So it's so just like the lozenge tiling, but then we are counting again the marginals of how many boxes we have in each slice, and we have this lower bound but it's not a very good lower bound in some sense, so it gives. So for some special type of partition triples, it would give this type of exponent, but you know, so Kronecker coefficient can be as large as square root of that factorial, so this is really far from. And then we conjectured that really the maximal Kronecker coefficient would already be here when we get three identical partitions, or symmetric, and this is going to be the same asymptotic that the overall maximum is achieved. So what we were able to prove is that instead of 1/2 is basically 1/16 somehow shows up, but it's still not. I mean, it's pretty far from the actual conjecture. And so there are other things people consider. There is the notion of reduced Kronecker coefficient, which is basically a direct generalization of the Littlewood-Richardson coefficients that I showed earlier, and which are a lot nicer. So the reduced Kronecker coefficient is just the Kronecker coefficient when we have three partitions. So if we fix this three lower partitions, so this is going to be alpha, and then basically we add one very long row with, and then whatever. So alpha, beta, and gamma are not forced to be of the same size at all, but we are forcing we are just making them the same size by adding a really long first row. So eventually, when we add more and more things to the first row, this will stabilize. It will be the same coefficient. And this is the reduced Kronecker coefficient. So people somehow believe that this would be nicer than the original Kronecker coefficient, especially that they directly reduce to Littlewood-Richardson when this identity here holds. And there was a conjecture that they also based something called the saturation property. So if we scale the partitions and this is actually positive, then the original thing was positive. This is true for the Littlewood-Richardson coefficient. So it turns out it's not. There is a not so hard counterexample, but because these are difficult to compute, so people didn't really see this. And then, of course, the question would be, again, what is the maximum for the same guys? And basically, the maximum is really the same. Square root of that. So there really as bad as the original Kronecker coefficients. And that's it. Thank you very much.
Questions? If you're in the chat, feel free to unmute yourself. Chat.
The last section where you're looking at the maximum, was there, I think I might have missed, is there like a natural reason to look at that, or is it just like it's like the most natural question?
It's the easiest question you can ask.
Fair enough.
But so okay, maybe a little bit more of a story that I didn't really tell, but when I was the Plancher L shape, that you probably know about. So that's basically that's where you look for the maximal possible, the standard Young Tableaux, so the maximal F lambda or asymptotic, this asymptotically maximal. So that's basically in some sense a tradition, and a lot of interesting things fall out of it. So yeah, so we do want to understand the range, whatever maximum, where is it achieved, and yeah.
That makes sense. Thanks.
Other questions?
So I have one. Is there any other property for the Kronecker coefficient, like multiplicity or concavity for the coefficient?
So there is one really nice property that is showed actually. So There is a multiplicity, and this is actually what we use in a lot of these results that I didn't talk about. So if we take a Kronecker coefficient which is positive and another one which is positive, well, let's call it lambda prime beta prime gamma prime. So if these are two are positive, then we can say that we can add these partitions pairwise as vectors, alpha plus alpha prime, beta plus beta prime, gamma plus gamma prime. And this is greater than or equal to the maximum of this two. So this is semi-group property or multiplicity, call it. And this is what we use actually to obtain all sorts of lower bounds. So as I said, so there is essentially only one explicit case where we know the asymptotics, and then we can construct other positive triples by various indications of this rule and combining the tables. So saturation doesn't hold concavity. So I mean, so most likely not. So people like conjecture.
It's easy to conjecture.
Yeah. And you get something.
Other questions? I had a question. So this is all for the Schur polynomials and with the Cauchy identity and generalized Cauchy identity. And I was wondering if, I mean, this is short and dark, but if this type of story generalizes for other symmetric polynomials like Spin-Hall-Littlewood or McDonald's, where you have a generalized Cauchy, or they have a version of the Cauchy identity, whether for those polynomials there's like generalized Cauchy identity.
So for those guys, a lot of the combinatorics doesn't carry over. It's exact because one of the biggest solvable problems in algebraic combinatorics is just to figure out to help prove that the McDonald polynomial, the modified McDonald polynomial expands positively in Schur function, for example. And so, where things become much more difficult from that point of view, and also the other. So actually, since Sender Cohen and Vadim Gorin did generalize some of the asymptotic formulas for McDonald polynomials. But then the combinatorics is not as natural. I mean, they would come into the vertex models and things like that, but it's basically they are created much. The recursive formulas are done for them.
And a generalized Cauchy identity where you take the product of three symmetric polynomials.
No, that's not done. That's like so this has representation theoretic meaning. So if you do it, we can plug in some other function with no idea what we get. Yeah.
All right. Well, join me in thanking Vera one more time. We have